an estimated 10,000 galaxies, each one a city of hundreds of billions of stars, each one separated from the next by distances your mind will refuse to hold. That photograph came from the James Webb Space Telescope, and the moment it was released, astronomers went quiet. We were already aware the universe was large. That awareness had been abstract, manageable. Webb made it concrete. Webb made it measurable. And what it measured was something that even the scientists who built it are still working to process. In the chapters ahead, we follow what Webb has actually found. Galaxies that existed before they should have. Black holes that grew faster than our models allow. A universe expanding faster than two independent methods of measuring it can agree on. And a boundary at the edge of the observable cosmos beyond which light will never reach us, no matter how long we wait. If you enjoy following science that genuinely unsettles our picture of reality, subscribe to Late Science. We cover the universe's strangest confirmed facts, and this one earns that word. The scale Webb revealed is real, verified, measured. Prepare yourselves. We begin. Point your finger at the night sky and pick a spot between two stars. A spot so small that a grain of sand held at arm's length would cover it completely. Blank space, as far as any previous telescope was concerned. Empty, unremarkable. James Webb stared at that spot for just over 12 hours. What came back was 10,000 galaxies. Every smear of light in that image, every spiral, every oval, every red-shifted blur, was an entire galaxy, a system of hundreds of billions of stars, separated from the next one by distances measured in millions of light-years, all of them packed into a patch of sky your fingernail could hide. That image, released in July of 2022, is called the Webb Deep Field, and the first thing it confirmed is that the universe is not mostly empty. It is mostly full. Everywhere you point, in every direction, at every depth, there are galaxies beyond galaxies beyond galaxies. The emptiness we imagined was always an illusion created by the limits of our instruments. To understand why that hit so hard, think about what came before. The Hubble Space Telescope produced its own deep field image back in 1995. That image also revealed thousands of galaxies. It was extraordinary at the time. But Hubble was working in visible light, and visible light tells only part of the story. A large fraction of the earliest, most distant galaxies are hidden behind clouds of gas and dust. Their light is stretched and dimmed by billions of years of travel. Hubble could sense them only faintly, like trying to read a sign through heavy fog. Webb works in infrared. It detects heat radiation that passes through dust clouds, the way a radio signal passes through a wall. What was fog to Hubble is transparent to Webb. That single difference meant Webb could see not just farther, but deeper into time. The galaxies in the Webb Deep Field include some of the oldest objects ever photographed. Some existed when the universe was less than 5% of its current age. 5%. The universe is roughly 13.8 billion years old. Some of what Webb photographed in that one image dates back over 13 billion years. You are looking at the early universe, a universe so young that the Milky Way, Earth, and every living thing on it did not yet exist in any form. And the count of 10,000 galaxies is for that one field alone. Astronomers estimate the observable universe contains somewhere between 100 billion and 2 trillion galaxies total. 2 trillion. Webb did not invent that number, but its early observations suggest the upper end of that range is closer to correct than we previously assumed. The universe is denser with galaxies than our best pre-Webb models predicted. That density has a consequence. If galaxies are more numerous than expected, the number of stars is correspondingly larger. If the number of stars is larger, the number of planets is larger. If the number of planets is larger, the surface area of potential worlds across the cosmos becomes a figure so large it has no meaningful comparison to anything in human experience. Webb's first image did not just update a number, it forced a recalibration of the entire framework. Every assumption built on the idea that we had a reasonable picture of how full the universe has turned out to be an underestimate. The grain of sand hid a cosmos inside it. And what Webb found inside the earliest of those 10,000 galaxies is where the real pressure begins. Because some of those ancient galaxies should not look the way they do. They should not even exist yet. Every time Webb opens its eye, it is looking into the past. That sounds like a metaphor. It is pure physics. Light travels fast, but the universe is incomprehensibly large. Light from the nearest star beyond our own takes over 4 years to reach us. Light from the center of the Milky Way takes around 26,000 years. Light from the nearest large galaxy, Andromeda, left its source over 2 million years ago. By the time any of that light reaches Webb's mirror, The object that produced it has already changed, moved, aged, or in some cases, ceased to exist entirely. Webb is positioned roughly 1 million miles from Earth, far beyond the Moon, sitting at a gravitational balance point that keeps it stable and in constant shadow. From there, it peers outward, and the farther it looks, the further back in time it reaches. The most distant objects Webb has confirmed are seen as they existed over 13 billion years ago, when the universe was only a few 100 million years old. That gap between then and now is almost impossible to hold as a real number. The universe was less than 3% of its current age. There were no planets in the solar system. There was no solar system. There was no Milky Way in anything like its current form. There were only the first generations of stars and the young galaxies pulling together around them. What Webb does is translate that ancient light into data. Its infrared detectors capture photons that have been traveling since before Earth existed and convert them into images and spectra that astronomers can analyze. The telescope is measuring the chemical composition, temperature, mass, and age of objects that no human and no prior instrument has ever examined directly. Before Webb, the view of the early universe came mostly from the Hubble Space Telescope and from a landmark observation called the cosmic microwave background, the faint afterglow of the Big Bang itself, measured in extraordinary detail by missions like the European Space Agency's Planck satellite. Those sources gave us a strong general model. They told us roughly how and when the first stars and galaxies should have formed. Webb is now testing that model directly, in detail, at the source, and the early results are already generating serious debate. Some galaxies Webb has photographed from the early universe appear too large, too structured, and too chemically evolved for their age. The model said they should still be assembling themselves. Webb found them already built. That gap between prediction and observation is the current frontier of cosmology. Researchers are working to understand whether the model needs adjustment, whether the age estimates for these galaxies have margins of error that could close the gap, or whether something more fundamental about how galaxies form is being missed. The debate is ongoing and unresolved as of early 2000-2005. But the time machine aspect of Webb carries a stranger implication beneath the science. When you look at a Webb image of a galaxy from 13 billion years ago, you are seeing a place that in the present moment no longer looks like that. It has had 13 billion years to evolve. It may have merged with other galaxies. Its stars may have aged and died. We have no way to see what it looks like right now, because the light carrying that information will not arrive for another 13 billion years. We are always seeing the universe as it was, never as it is. Webb sharpened that fact more than any instrument before it, and it sharpened something else too. A problem with the galaxies it found in that ancient light that our leading theory of cosmic history cannot yet explain. In early 2002-03, a team of astronomers published a paper that described 6 galaxies in Webb's early observation data as, in their own words, ununiverse breakers. That phrase got attention. The science behind it deserves the same. The standard model of cosmology, the framework that has guided our understanding of the universe's structure for decades, predicts a clear sequence for how galaxies build themselves. In the very early universe, matter was spread relatively smoothly. Gravity pulled it together into clumps. Those clumps formed the first small, irregular galaxies. Over hundreds of millions and then billions of years, those small galaxies merged, accumulated more gas, formed more stars, and gradually grew into the large, structured galaxies we see in the universe today. That process takes time, enormous amounts of it. A galaxy the size and mass of the Milky Way should take billions of years to assemble. Webb found galaxies in the early universe, existing when the cosmos was between 500 million and 700 million years old, that are already massive. One candidate observed in Webb data appears to contain as many stars as the Milky Way does today, packed into a galaxy that existed less than 700 million years after the Big Bang. According to the Standard Model's timeline, that galaxy should not be anywhere near that size yet. It gets more specific than mass alone. Some of these early massive galaxies appear to already contain older stellar populations, meaning stars that formed even earlier and have already aged. That pushes the implied timeline of their assembly back even further, into a window the Standard Model considers implausible. Astronomers are careful about these findings. The word candidate appears frequently in the literature because confirming the exact distance and mass of a very faint, very distant galaxy requires detailed spectroscopic analysis that takes time to complete. Some early candidates have had their estimates revised after closer examination. The scientific process here is still running, but as of 2024, Several of these massive early galaxies have received spectroscopic confirmation of their distance and approximate mass, and they remain genuinely difficult for current models to explain. The tension is real and being actively debated. One proposed explanation is that star formation in the very early universe was more efficient than we modeled. Stars may have formed from the available gas at a faster rate, building mass quickly before feedback mechanisms, the radiation and winds produced by new stars, had time to slow the process down. This is a plausible adjustment to the model, and it does not require abandoning the larger framework. Another possibility under discussion is that the initial density variations in the early universe were not perfectly uniform, and some regions had enough of a head start that galaxies in those areas grew faster than the average case the model describes. What makes this genuinely significant is not that the model is wrong. Models in science are tools, and tools get refined. What makes it significant is that Webb is producing observations precise enough to stress test the model in ways we could never manage before. Every refined measurement tightens the constraint on what the early universe could and could not have done. The galaxies Webb found are real. Their size is measured, and the question of how they got so large, so fast, is one of the most active research questions in cosmology right now. The answer, whatever it turns out to be, will change the timeline of how the universe we live in actually assembled itself. To see the farthest galaxies Webb has confirmed, light had to travel for over 13 billion years. That number appears constantly in cosmology discussions, and it can start to feel routine. It should not. Consider what 13 billion years of travel actually means for a photon. A photon of light moves at roughly 186,000 miles per second. It circles the Earth about 7.5 times in 1 second. In a single year, it crosses roughly 5.9 trillion miles. Multiply that by 13 billion, and you have a distance so large that every unit of measurement familiar to daily life becomes useless as a reference. Now consider that the photon did not travel that distance through still space. The universe was expanding the entire time. The space the photon was crossing was itself stretching. The source that emitted the photon was receding as the light traveled. By the time that light arrived at Webb's mirror, the galaxy that produced it is now estimated to be over 40 billion light-years away from us, even though the light only took 13 billion years to arrive. That apparent contradiction resolves when you understand that distance in an expanding universe is measured differently depending on when you measure it. The distance to the source at the moment the light was emitted was much smaller. The distance to the same source today, accounting for all the expansion that has happened since, is far larger. Both numbers are correct in their respective contexts. Webb captures that ancient light using a primary mirror 21 feet across, made of 18 hexagonal gold-coated beryllium segments that unfold in space like a mechanical flower. Each segment was polished to a precision of nanometers, fractions of a millionth of an inch, because any surface irregularity at that scale would smear the faintest signals into noise. The telescope operates at around -448 degrees Fahrenheit. That temperature is necessary because Webb's detectors are sensitive to infrared radiation, which is essentially heat. If the telescope itself were warm, its own heat would blind its sensors. At its operating temperature, Webb is colder than the surface of Pluto. It is colder than most places in the known solar system. All of that engineering exists for one purpose: to catch photons that have been traveling for billions of years and arrive at the mirror with almost no energy left. Photons so faint that Webb's detectors need microseconds to register them. Yet those photons carry real information. Wavelength tells us the galaxy's recession speed. The spread of wavelengths across the spectrum tells us what elements are present. The pattern of that spread tells us the temperature and age of the stars inside. A single photon, 13 billion years old, carries the fingerprint of a galaxy that formed before our planet's star existed. Webb is designed to read that fingerprint with enough precision to tell the difference between a galaxy that formed 300 million years after the Big Bang and one that formed 500 million years after. That distinction, 200 million years across a span of 13 billion, is within Webb's measurement capability. The implications of that precision are what the following chapters carry. Because when you can measure ancient light that accurately, every number you produce either confirms or challenges the model of how the universe evolved. And several of Webb's numbers are doing something more than confirming. Before Webb, the estimate of 200 billion galaxies in the observable universe was already a number that resisted comprehension. Then Webb's early observations started suggesting that estimate may be too low. A study published in 2016 using Hubble data, before Webb launched, had already revised the galaxy count upward to around 2 trillion, based on extrapolations from deep field images and models of galaxy evolution over time. Webb's observations are now feeding into a sharper version of that picture. Here is the mechanism behind that revision. Early in the universe's history, galaxies were smaller and more numerous. Many of those early dwarf galaxies merged over billions of years to form larger galaxies like the Milky Way. But the smaller, earlier galaxies that fed those mergers existed in enormous quantities. Older telescopes could not see most of them because they were too faint and too distant. Webb can see them, and they are everywhere. When astronomers look at Webb's deep field data and count the density of galaxies at various distances, they find that the universe at early epochs was populated far more densely with small, faint structures than our previous observations could confirm. Those structures are real. They formed, they evolved, they merged. The universe we live in today is the accumulated product of a history far more crowded than we were measuring. That crowding has a direct consequence for the cosmic web, the large-scale architecture of the universe. On the largest scales, galaxies do not distribute themselves randomly. They cluster along enormous filaments of dark matter, with vast empty regions called voids between them. The filaments intersect at nodes where the largest galaxy clusters sit, containing thousands of galaxies bound together by gravity. Webb cannot image the full cosmic web directly, because the scales involved span billions of light years and no single instrument can capture that. But Webb's precise observations of individual galaxy clusters, their distances, masses, and star formation histories, feed into the maps that cosmologists use to model the Webb structure. And those maps, refined by Webb data, show a universe where the filaments are denser and the nodes are more heavily populated than the pre-Webb estimates implied. The voids between filaments are also real and confirmed. Surveys of the large-scale universe have identified regions hundreds of millions of light-years across that contain almost no galaxies. The Boots void, one of the largest known, spans roughly 330 million light-years. Inside it, galaxies are extraordinarily rare. The contrast between these voids and the dense filaments around them defines the universe's texture at the largest scale we can map. What Webb contributes to this picture is the historical dimension. By seeing galaxies across a wide range of cosmic ages, Webb lets astronomers watch the cosmic web assemble over time. The early universe shows smaller, more scattered structures. Later epochs show those structures pulling together. The process is gravitational, slow by human standards, and enormous in every physical dimension. 2 trillion galaxies, each containing hundreds of billions of stars, arranged along a web of dark matter filaments, stretching across the observable universe. And the observable universe is itself only the portion of space from which light has had time to reach us. What lies beyond that boundary is where the scale becomes genuinely unresolvable. The universe is expanding. That has been confirmed since Edwin Hubble's observations in the 1920s. The rate of that expansion is described by a number called the Hubble constant, measured in kilometers per second per megaparsec, which is essentially a statement of how fast galaxies are receding from each other per unit of distance. Measuring that number precisely has been one of cosmology's central goals for decades. Webb stepped directly into that effort, and what it found made a long-running problem harder to dismiss. There are 2 main methods for measuring the expansion rate. The first works backward from the early universe. Scientists use the detailed pattern of the cosmic microwave background, the faint afterglow light from roughly 380,000 years after the Big Bang, measured with extraordinary precision by the Planck satellite. Running the physics forward from that early state gives a predicted expansion rate today of around 67 kilometers per second per megaparsec. The second method measures the expansion rate directly in the local universe. Astronomers use a chain of distance measurements called the cosmic distance ladder. The ladder starts with parallax measurements of nearby stars, moves to pulsing stars called Cepheid variables, whose brightness cycles reveal their true luminosity, and then uses that calibration to measure the distance to supernova in far galaxies. Those supernovae distances, combined with galaxy recession speeds, give an expansion rate of around 73 kilometers per second per megaparsec. 67 versus 73. Those numbers do not agree, and the disagreement has been called the Hubble tension for years. Some researchers hoped it was a measurement error that better data would resolve. Webb was specifically used to check the Cepheid variable measurements that anchor the local distance ladder. Prior telescopes had measured Cepheids in nearby galaxies, but their resolution was limited in crowded galactic regions, potentially introducing blending errors where multiple stars were accidentally measured as one. Webb's sharper resolution can separate individual Cepheid stars in those crowded fields with far greater precision. The result published in 2203 by a large team led by Nobel laureate Adam Rees, used Webb to recheck Cepheid measurements in multiple galaxies. They found that the Hubble Space Telescope's Cepheid measurements were largely accurate. The blending errors were smaller than feared. The local expansion rate measurement did not shift significantly towards 67. The Hubble tension remained. Webb made it more precise, which made it harder to explain away. A tension of that kind, between two carefully measured values that both appear correct on their own terms, is a serious problem in physics. Either the cosmic microwave background analysis is missing something, or the local distance ladder has a systematic error that even Webb's precision has not yet found. Or there is a feature of the universe's history or composition that the standard model does not currently include. Proposed solutions range from adjustments to the properties of dark energy in the early universe, to the existence of an unknown component called early dark energy that temporarily altered the expansion rate before recombination, to more exotic possibilities that remain at the theoretical stage. None of these proposals has been confirmed. The tension is real, measured by multiple independent teams, and unresolved as of 2025. Webb's role in this debate is to keep sharpening the measurements. Every additional Cepheid calibration, every improved distance to a galaxy hosting a supernova, narrows the uncertainty. And a narrower uncertainty that still shows a gap is a more serious challenge than a wide one. The Hubble tension is 67 versus 73. Those two numbers, separated by 6 units on a scale measuring cosmic expansion, represent one of the most serious, unresolved problems in modern physics. Understanding why requires understanding what the disagreement actually implies about the universe's history. The cosmic microwave background method is not just a measurement of light. It is a full physical model. Scientists take the detailed temperature variations in that ancient light, which are tiny, around 1 part in 100,000, and fit them to a cosmological model that includes the amounts of ordinary matter, and dark energy in the universe. The expansion rate comes out of that fit as a derived value. When Planck measured it, the answer was close to 67. The local distance ladder method is independent. It does not use the cosmic microwave background at all. It builds up from direct geometric measurements of nearby stars, extends to Cepheid variables in nearby galaxies, and then reaches into the distant universe using type AI supernovae, a class of stellar explosion that produces a consistent peak brightness, making them reliable distance markers. When multiple teams use this chain, the answer is close to 73. These two methods are independent in the sense that they use completely different physics, different instruments, and different objects. If they give different answers, one of 3 things is true. There is a systematic error in one method that has not been identified. There is a systematic error in both methods that push in opposite directions. Or the universe has a feature that causes the early expansion rate and the late expansion rate to genuinely differ from what a simple model predicts. That third option is what makes the tension scientifically exciting and genuinely unsettling. If the universe's expansion rate evolved in a way the standard model does not capture, it implies the model is incomplete. It implies something happened to dark energy, or dark matter, or the curvature of space, or some other component between the early universe and today that we are not accounting for. Webb's contribution is precision. It has sharpened the local measurement without moving it toward the early universe value. Every time measurement precision improves and the tension holds, it becomes less likely to be a measurement artifact and more likely to be real physics. The proposal of early dark energy is one of the most discussed adjustments. In this framework, an additional component of energy existed in the early universe that increased the expansion rate briefly before disappearing or weakening. This would reduce the distance to the surface of last scattering used in the cosmic microwave background analysis, which would raise the inferred expansion rate from 67 towards something closer to 73. But early dark energy also changes other predictions that currently agree well with observations, so adding it creates new problems as it solves the tension. Researchers are also examining whether the supernova distance ladder has systematic biases related to the environments where type Ia supernovae occur in different types of galaxies. Some work suggests that supernovae in older stellar environments may have slightly different intrinsic properties than those in younger environments, which could affect the distance calibration. Every possible fix requires data to test it. Webb is providing that data. The Hubble tension is the clearest sign currently available that our model of the universe, successful and precise as it is, may be missing a chapter. What fills that chapter will reshape how we describe everything Webb is measuring. Take the universe at its largest scale and look away from the galaxies for a moment. Look at what is between them. Most of the volume of the observable universe is empty. genuinely, profoundly empty. The regions called cosmic voids are not small gaps. They are enormous structures, each spanning hundreds of millions of light years in diameter, where the density of galaxies drops to nearly zero. Inside a void, you could travel in any direction for tens of millions of light years without passing a single large galaxy. The Boots Void is one of the most studied. Discovered in 1981 during a survey of galaxy positions, it spans roughly 330 million light years across. When it was first identified, the scale was difficult to accept. At that time, structures of that size were not predicted by existing models of how matter clusters under gravity. Voids are not violations of physics. They form because gravity is selective. In the very early universe, the distribution of matter was almost uniform, but not perfectly so. There were regions of slightly higher density and regions of slightly lower density. Gravity amplified those differences. The denser regions pulled in surrounding matter, forming the filaments and galaxy clusters we see today. The lower density regions lost matter to their surroundings and became emptier over time. The voids we see now are the grown-up versions of those early low-density regions, stretched and deepened by billions of years of gravitational drainage. Webb does not image voids directly, because a void is defined by the absence of bright objects. But Webb's precise measurements of galaxies at the edges of known voids, and in the filaments surrounding them, contribute to the three-dimensional maps that reveal the large-scale structure. Every confirmed galaxy distance is a data point in the cosmic map. Webb adds data points with far greater precision and at far greater distances than its predecessors. What those maps show at the largest scales is a structure that cosmologists call the cosmic web. Filaments of dark matter and gas stretch across billions of light years. Galaxies form along those filaments, denser near the intersections. Between the filaments sit the voids. The whole architecture looks if you could see it in 3 dimensions like a sponge, with solid walls and enormous hollow chambers. The scale of individual voids challenges the standard cosmological model in a subtle way. Some of the largest void-like underdensities in the observed universe appear larger than simulations predict they should be under the standard framework. The cold spot in the cosmic microwave background, a region of the sky that appears slightly cooler than average, has been tentatively linked to a supervoid along the line of sight. A void so large it cooled photons passing through it by a gravitational effect. The connection remains debated and unconfirmed. What is confirmed is the overall architecture. The universe at the largest scales is not smoothly filled. It is arranged in a web of matter, surrounding vast emptiness, and the contrast between the two is more extreme than our early models of galaxy formation predicted. Webb's precision feeds that map, and the map, the more accurately it is drawn, keeps showing a universe where the structure is sharper, the voids deeper, and the filaments denser than the smooth early universe models would suggest. Something is pulling matter into tighter arrangements than expected. That something has a name. It has never been directly detected, and it turns out to be the dominant ingredient of the universe. The cosmic web has a skeleton. It cannot be photographed directly. It emits no light, reflects no light, and interacts with almost nothing that our instruments are designed to detect. Astronomers infer its presence from the way galaxies move, cluster, and arrange themselves across billions of light years. That skeleton is dark matter. Dark matter is not a theoretical convenience. Its existence is supported by multiple independent lines of evidence going back decades. Galaxies rotate in ways that their visible mass cannot explain. The rotational speeds of stars at the outer edges of galaxies are too high for the amount of ordinary matter present to hold them gravitationally. Something additional, invisible, must be providing the gravitational pull. Galaxy clusters also reveal the presence of dark matter through a different mechanism. When hot gas in a cluster is mapped using X-ray telescopes, and the mass needed to gravitationally confine that gas is calculated, the visible galaxies in the cluster account for only a fraction of the required mass. The rest is dark matter. The most visually striking evidence comes from gravitational lensing. When light from a distant galaxy passes near a massive object, such as a galaxy cluster, gravity bends the path of the light. This bending creates distorted, stretched, or multiplied images of the background galaxy. The amount of bending reveals the total mass of the lens, including mass that produces no light. By mapping lensing distortions across large areas of sky, astronomers can reconstruct the distribution of dark matter in 3 dimensions. Webb is exceptionally good at gravitational lensing studies. Its resolution and sensitivity allow it to detect the subtle distortions produced by dark matter halos around clusters and even around individual massive galaxies. Webb's lensing maps confirm that dark matter halos are present, that they are more massive than the visible galaxies they surround, and that their shapes and distributions match the predictions of the standard cold dark matter model reasonably well. That confirmation is significant. It means that despite dark matter's mysterious nature, its gravitational behavior is consistent and predictable. The model works in that sense. Dark matter makes up roughly 27% of the total energy content of the universe, according to the best current measurements from the Planck satellite and other surveys. Ordinary matter, everything made of protons, neutrons, and electrons, including every star, planet, gas cloud, and living thing, makes up roughly 5%. The remaining 68% is dark energy. The cosmic web is dark matter's visible output. The filaments that connect galaxy clusters, the halos that wrap individual galaxies, the scaffolding on which all baryonic structure is built, these are dark matter. Webb maps its gravitational effects with precision that prior telescopes could not match, but dark matter itself has never been directly detected in a laboratory. No experiment has caught a dark matter particle interacting with ordinary matter in a controlled setting. Its nature, what it actually is at the particle physics level, remains completely unknown. Webb can map where dark matter is and how it clusters. It cannot tell us what dark matter is made of. That question is one of the deepest in physics, and answering it would represent a fundamental expansion of the known laws of nature. The web is real. Its builder is a mystery. And it turns out the web is assembling itself faster than the simulations we use to model it would predict. When Webb began observing galaxy clusters in the early universe, the images it returned showed something that simulations of structure formation were not fully prepared for. Galaxy clusters, gravitationally bound systems containing hundreds to thousands of galaxies, appear to have been assembling their mass earlier and faster than the standard model predicts. Structure formation in cosmology follows a bottom-up logic. Smaller objects form first. Gravity then draws them together into larger objects over time. Dark matter clumps form first, drawing in gas to form stars and galaxies. Those galaxies cluster together into groups, and groups grow into clusters. The whole process is hierarchical, each step building on the last, and the timescales involved are long. Webb has observed protoclusters, the predecessors of modern galaxy clusters, at distances corresponding to the universe at around 1 to 3 billion years of age. Some of these early structures are already more massive and more spatially concentrated than standard cold dark matter simulations suggest they should be at those epochs. One well-studied case involves a system observed by Webb, where multiple massive galaxies appear to be clustered together in the early universe, at a density that, if confirmed as a gravitationally bound structure, would represent a cluster assembling much earlier and faster than the leading models expect. Follow-up observations are ongoing, and the precise mass and binding state of such systems require careful spectroscopic confirmation. The important point is not that one system is anomalous. Anomalies happen. The point is that Webb is finding these early massive structures with a frequency that, taken together, suggests structure formation in the early universe was more efficient and more rapid than our models capture. One mechanism that could explain this is an enhancement in the small-scale power of the initial density fluctuations, the tiny variations in the early universe's density that seeded all later structure. If those fluctuations were slightly stronger on small scales than the standard model assumes, gravity would have pulled matter together faster in localized regions, building massive structures earlier. Another avenue being explored is whether feedback from the first massive black holes, the supermassive black holes that Webb has found, already present in the early universe, altered star formation and gas distribution in ways that affected how quickly surrounding structure assembled. Black hole feedback is known to regulate star formation in galaxies today. Its role in the early universe is an active area of modeling. Simulations of cosmic structure formation are enormously complex. They require modeling gravity, gas physics, star formation, supernova, radiation, and black hole activity across cosmic time. The best current simulations, including projects like Illustris TNG and Eagle, reproduce many observed features of the universe well. But Webb's early epoch observations are providing data at an accuracy and depth those simulations were not specifically calibrated against. That gap between simulation and observation is where the science is moving forward. Researchers are revising simulations to test whether parameter adjustments can match what Webb observes, or whether more fundamental changes to the model are needed. The universe apparently built its largest structures with less time than the instruction manual allowed. That efficiency points towards something in the initial conditions, or in the physics of the early universe, that the current model is still working to fully account for. And if structure assembled faster than expected, the objects at the centers of those structures grew faster too. No one has ever directly seen a population 3 star. They are a theoretical prediction, the hypothetical first generation of stars that formed in the early universe before any heavy elements existed. Webb may be the first instrument capable of detecting their indirect signature. In the very early universe, immediately after the Big Bang, the only elements that existed in significant quantities were hydrogen, helium, and trace amounts of lithium. Everything heavier, carbon, oxygen, iron, calcium, every element that makes up planets and living things, was created inside stars and scattered by stellar explosions. The very first stars formed from a universe that contained only those three lightest elements. Stars made purely from hydrogen and helium would have had very different properties from stars today. Without heavy elements to radiate energy efficiently during formation, these early stars would have needed to be much more massive to reach the temperatures required for nuclear fusion. Theoretical models suggest population 3 stars may have been tens to hundreds of times the mass of our stellar neighbor, making them extraordinarily luminous and short-lived. They would have burned fast and died in powerful explosions, seeding the surrounding gas with the first heavy elements. Webb cannot image an individual population 3 star directly. They existed too long ago, in too distant a region, and even the most luminous individual star is too faint at cosmological distances for direct detection. What Webb can look for is the chemical signature they left behind. When population 3 stars exploded, they enriched the surrounding gas with a specific pattern of heavy elements. That pattern differs from the enrichment produced by later, lower-mass stellar generations. If Webb can measure the detailed chemical compositions of very early galaxies, the mixture of elements present in those galaxies can be compared to theoretical predictions of population 3 enrichment. In 2003, Webb detected a particularly strong emission line in the spectrum of a galaxy existing around 400 million years after the Big Bang. The line corresponds to ionized helium, and its unusual strength is consistent with, though not proven to be caused by, the presence of extremely hot, very massive stars of the kind population 3 stars are predicted to be. The finding is tentative. It requires further analysis and cannot yet be definitively attributed to population 3 stars versus other exotic possibilities. A separate search strategy involves looking for the chemical abundances in the outer regions of very old, nearby stars, which can preserve records of the early enrichment environment they formed in. Webb contributes to this by providing better context for the early universe's chemical evolution. The population 3 question matters because these stars were the hinge point between a universe of only light elements and a universe capable of making planets and life. Everything heavier than lithium in your body traces its origin back through a chain of stellar generations that began with those first invisible stars. If Webb confirms their chemical signature, even indirectly, it would close a chapter in the story of cosmic chemistry that has been open since the theory of stellar nucleosynthesis was first developed. The first stars may leave traces. They may not. Webb is the first instrument positioned to tell the difference. And while it searches for the faintest chemical whispers of the universe's first lights, it has already found something else in those early epochs that nobody expected to be there yet. A galaxy the mass of the Milky Way took billions of years to build. That is the standard story, and for most of the universe it appears to be correct. Webb found exceptions. Multiple of them. The Milky Way contains somewhere between 100 billion and 400 billion stars. It has been building that population for most of the universe's 13.8 billion year history, through a combination of ongoing star formation and galactic mergers. The process was slow, hierarchical, and long. Webb has photographed galaxies in the early universe, existing when the cosmos was between 500 million and 1 billion years old, that appear to contain stellar masses comparable to or exceeding the Milky Way's current mass. One candidate, analyzed in a study published in 2023 and referred to informally by researchers as one of the universe breakers, appeared to contain a mass of stars roughly equivalent to the Milky Way, compressed into a galaxy that existed when the universe was about 700 million years old. For that galaxy to contain that many stars at that age, star formation would need to have proceeded at a rate far exceeding what current models predict for that cosmic epoch. The galaxy would have had to convert available gas into stars, with an efficiency that the standard framework, calibrated on galaxies we can study in more detail at closer distances, does not accommodate. Spectroscopic confirmations, which pin down the precise distance and allow better mass estimates, have been completed for several of these candidates. The results have moderated some initial estimates, where early photometric redshifts overestimated distances in a few cases, but a core group of massive early galaxies remains confirmed and anomalous. There is a connected observation that deepens the problem. Some of these massive early galaxies appear to already be quiescent, meaning they have stopped forming stars. They consumed their available gas quickly, formed their stars fast, and then went quiet, all within the universe's first billion years. Quiescent galaxies at such early epochs are another category that standard models struggle to produce in the quantities Webb is finding. One framework for understanding this involves the role of supermassive black holes. A black hole, at the center of a galaxy, as it feeds on surrounding gas, releases enormous amounts of energy through jets and radiation. This process, called active galactic nucleus feedback, can heat the surrounding gas and prevent it from cooling and collapsing into new stars. If early galaxies hosted particularly active central black holes, that feedback could have shut down star formation fast, producing a quiescent massive galaxy at an early epoch. This is plausible and consistent with other Webb observations of early active galactic nuclei, but it requires that supermassive black holes grew to sufficient mass fast enough to produce this feedback, which brings in a separate problem of early black hole growth addressed by what Webb has found at galactic centers. The picture emerging from multiple lines of Webb evidence is of an early universe that was more productive, more violent, and more rapidly evolving than the calm, gradual story the standard model tells. The mechanisms driving that productivity are not yet fully understood, but every new Webb spectrum from the early universe adds another constraint, and the constraints are tightening around a timeline that the current model is increasingly struggling to reproduce. Some of the most powerful telescopes in the universe are galaxies themselves. Webb has learned to use them. When light from a very distant object passes near a massive galaxy cluster between it and us, the gravity of that cluster bends the light. The bending is not random. Gravity curves space, and light follows that curvature, deflecting toward the mass, just as a lens bends light toward its center. The result is that the cluster acts as a gravitational lens, magnifying and distorting the background object's light and delivering it to our detectors brighter than it would otherwise appear. This effect, called gravitational lensing, was predicted by general relativity and first confirmed observationally in 1979. Webb uses it as a core observational strategy. The advantage is measurable. A background galaxy that would be too faint for even Webb to detect unaided can be amplified by a factor of 10, 20, or in extreme cases more than 50, through a powerful gravitational lens. That amplification is not a distortion of the science. The light is real. The photons are the same ones that left the distant galaxy. Gravitational lensing simply redirects more of them toward the detector. Webb has targeted several known powerful lensing clusters, specifically to peer at the background universe behind them. One of the most productive of these is a cluster called El Gordo, a Spanish phrase meaning the fat one, a massive cluster in the southern sky that lenses multiple background galaxies. Another is the cluster Abell 2744, known informally as Pandora's Box, which Webb imaged in early release observations, revealing hundreds of background galaxies distorted into arcs and streaks by the cluster's gravity. Behind these lensing clusters, Webb finds galaxies that would otherwise be completely invisible at current sensitivity levels. The lensing effectively extends Webb's reach into epochs and distances that would otherwise remain inaccessible. There is a precise elegance to this. The most massive objects in the universe, the galaxy clusters that represent the peaks of cosmic structure formation, become tools for illuminating the universe's earliest and faintest objects. The architecture of the cosmos at large scales enables the science of the cosmos at small scales. Webb also uses lensing to measure dark matter distributions. The shapes of the distorted background arcs encode information about the mass distribution of the lensing cluster. By modeling those shapes, astronomers reconstruct where the mass in the cluster is concentrated, including the dark matter that surrounds and extends far beyond the visible galaxies. These lensing mass maps confirm the existence of dark matter halos and reveal their detailed structure with precision that direct observation cannot achieve. One striking application of this is the study of small-scale dark matter structures. Theory predicts that dark matter halos should contain numerous smaller subhalos. Gravitational lensing of background light by individual subhalos within a larger cluster produces detectable perturbations in the lensed arcs. Webb's resolution is fine enough to detect some of these perturbations, providing a new observational test of dark matter models at scales that were previously inaccessible. Every lensing observation Webb performs is simultaneously an observation of the lens and the object behind it, the near and the far, the present structure and the ancient signal, captured in a single image. And behind some of those lenses, in the stretched arcs of gravitationally bent light, Webb has found individual stars inside galaxies over 10 billion light-years away. Stars, not galaxies, individual stellar objects, visible only because lensing amplification makes the impossible momentarily possible. Everything discussed so far has involved the universe at its largest scales, the scale of galaxies, clusters, and cosmic time. Webb operates at those scales with precision no instrument has matched. But Webb also works at the other end of the size range, and what it finds there is connected to a question that may matter more personally than the mass of a distant galaxy cluster. Are there other worlds with the right chemistry for life? Webb cannot image exoplanets directly in most cases. Planets around other stars are tiny compared to the stars they orbit, and they are overwhelmed by stellar light. But Webb uses a technique called transmission spectroscopy to analyze what exoplanet atmospheres are actually made of. When a planet passes in front of its star from Webb's perspective, a small fraction of the star's light filters through the planet's atmosphere before reaching Webb's detectors. Different molecules in the atmosphere absorb different wavelengths of that light. By comparing the spectrum of the star alone to the spectrum taken during the planet's transit, astronomers can identify which wavelengths are absorbed, and from that, which molecules are present. Webb's infrared sensitivity makes it far more capable at this technique than any prior space telescope. In 22,000, Webb detected carbon dioxide in the atmosphere of a planet called WASP 39b, a gas giant orbiting a star roughly 700 light-years away. This was the first clear, detailed detection of carbon dioxide in an exoplanet atmosphere, and it demonstrated that Webb could identify molecules that are chemically significant for astrobiology. Since then, Webb has detected water vapor, sulfur dioxide, and sand-like silicate particles in various exoplanet atmospheres. The sulfur dioxide detection in WASP 39b was particularly notable because it was produced by a photochemical reaction between molecules driven by starlight, a process called photochemistry. Detecting the products of atmospheric chemistry, not just the raw molecules, means Webb is reading the active physical processes happening in another world's sky. The targets that matter most for the life question are rocky planets in the habitable zones of their stars, regions where liquid water could exist on a surface. These planets are smaller and cooler than gas giants, making their atmospheric signals harder to detect. Webb is currently conducting observations of rocky planets in the TRAP PIST-1 system, a set of 7 Earth-sized planets orbiting an ultra-cool dwarf star about 40 light-years away. Early Webb observations of TRAP PIST-1c, the second planet in the system, measured the planet's thermal emission and found it consistent with a bare rocky surface, with little or no thick atmosphere. That result does not rule out life on the other planets in the system, and observations of the others are continuing. The significance here is that Webb is the first instrument capable of characterizing rocky exoplanet atmospheres at all. Every observation is a new measurement in a territory that was completely inaccessible before 22,002. If Webb finds a rocky planet in a habitable zone, with an atmosphere showing oxygen, methane, and carbon dioxide simultaneously, that combination would be a potential biosignature, a chemical signal that is difficult to produce without biological processes. No such detection has been made. The search is active. The same telescope mapping galaxies 13 billion light-years away is also reading the air of worlds 40 light-years from Earth. That range of scale, from the edge of the observable universe to the nearest potentially habitable planets, is Webb operating exactly as designed. One of the most significant shifts in our understanding of the universe over the past 30 years is the realization that planets are ordinary. They are a routine outcome of the process that forms stars. Wherever a star forms, the disk of gas and dust surrounding it almost always produces planets. Before 1995, no planet outside the solar system had been confirmed. The first confirmed detection of a planet orbiting a star similar to our own came that year. In the decades since, the Kepler Space Telescope and the Transiting Exoplanet Survey satellite have confirmed over 5,500 exoplanets, with thousands more candidates awaiting confirmation. The rate of discovery has revealed a statistical pattern. Planets are common around virtually all types of stars. Small rocky planets appear to be especially frequent. Estimates derived from Kepler survey data suggest that on average, every star in the Milky Way hosts at least one planet. Some surveys suggest the average is higher than one. Webb builds on this by characterizing what those planets are like, rather than simply detecting their existence. The transit spectroscopy technique Webb applies moves the science from counting planets to understanding them. The question shifts from how many to what kind. Apply that frequency to the galaxy. The Milky Way contains an estimated 100 billion to 400 billion stars. If each hosts at least one planet, The number of planets in the Milky Way alone is in the hundreds of billions. If a fraction of those orbit in habitable zones where liquid water could exist, and current estimates suggest somewhere between 10 and 40% of stars host a planet in or near the habitable zone, the number of potentially interesting worlds is still enormous. Scale that to the observable universe. 2 trillion galaxies, each containing hundreds of billions of stars, each star likely hosting at least one planet. The arithmetic produces a number so large it has no human reference point. Quintillions of planets. The figure is not speculative. It follows directly from the observed statistics of planet formation, combined with the confirmed galaxy counts. Webb's atmospheric studies are beginning to map the diversity of those worlds. Gas giants show a wide variety of chemical compositions. Some have clear atmospheres. Some are shrouded in thick cloud layers that block spectroscopic analysis. Some show evidence of active photochemistry. Some have clouds made of silicate minerals that rain solid particles downward through the atmosphere. Rocky planets are harder to study, and Webb's data on them is still accumulating. The TRAPPIST-1 system remains the primary target because its planets are among the most observable rocky exoplanets known. The host star is small and cool, which means its planets pass in front of it frequently, and the planet-to-star size ratio is relatively favorable. The broader implication of the planet frequency finding is a shift in how we frame the question of life in the universe. A generation ago, the question of whether life existed elsewhere was partly a question of whether planets even existed elsewhere. That question is answered. Planets are everywhere. The remaining questions are about chemistry, atmospheric stability, and the presence of the conditions that allow complex chemistry to persist over geological timescales. Webb is the instrument positioned to address those questions, world by world, observation by observation. And some of those worlds orbit stars that are not calm, quiet stellar neighbors. Some orbit engines of energy output so extreme that they illuminate their host galaxies from a single point at the galactic center. At the center of some galaxies, a concentration of energy exists that outshines every star in that galaxy combined. Billions of stars, each producing the energy output of an entire stellar fusion reactor, summed together and still overwhelmed by a single point at the galactic core. These objects are called quasars, and Webb is studying them in the early universe with a clarity no prior telescope achieved. A quasar is powered by a supermassive black hole, actively feeding on surrounding gas and dust. As material falls toward the black hole, it forms an accretion disk, a swirling, superheated ring of infalling matter that reaches temperatures of millions of degrees. At those temperatures, the disk radiates intensely across the electromagnetic spectrum, including visible light, ultraviolet radiation, and X-rays. In many quasars, powerful jets of plasma shoot outward from the black hole's poles at velocities close to the speed of light, extending for hundreds of thousands of light years beyond the galaxy. The energy output of the most luminous quasars is staggering in measurable terms. The most powerful quasars observed radiate energy equivalent to the combined output of trillions of stars. They are visible across cosmological distances, and, in fact, were among the first objects to be confirmed at extreme distances using redshift measurements in the 1960s. Webb adds the ability to study quasars in the early universe with unprecedented spectral detail. By analyzing the light from quasars that existed when the universe was less than 1 billion years old, Webb can measure the mass of the central black hole, the rate at which the black hole is accreting material, and the chemical composition of the gas surrounding it. What Webb has found in this analysis reinforces a problem already identified by earlier telescopes. The supermassive black holes powering early quasars are too massive for their age. Black holes grow by accreting mass. There is a physical limit on how fast a black hole can accrete, set by the balance between gravity pulling material in and radiation pressure pushing it back out. This limit is called the Eddington limit. If a black hole accretes at the maximum possible rate, the time required to grow from a stellar mass black hole, a few times the mass of a star, to a supermassive black hole billions of times that mass, is longer than the age of the universe at the epoch where Webb finds them. The math does not close. Proposed solutions include the idea that the first black holes seeded in the early universe were already massive, forming not from individual stellar collapses, but from the direct collapse of large gas clouds. Another proposal is that early black holes experienced episodes of super Eddington accretion, exceeding the theoretical limit for brief periods under specific conditions. Both mechanisms are theoretically possible and are being modeled, but neither has been directly confirmed. What is confirmed is the existence of billions of solar mass black holes in the universe's first billion years. Webb has now identified several of them with spectroscopic precision, Each one represents a gravitational engine of a scale that restructures the galaxy surrounding it, drives out gas that could have formed stars, and shapes the chemical environment of billions of light years of surrounding space. The most luminous things in the universe are powered by objects that swallow light itself, and those objects were already fully operational when the cosmos was only a fraction of its current age. A black hole at the center of the Milky Way is called Sagittarius A star. It has a mass of roughly 4 million times the mass of a star like our own. It is largely dormant today, occasionally accreting small amounts of matter, but producing nothing like the luminous output of an active quasar. Webb has found black holes in the early universe with masses billions of times larger than Sagittarius A star. Black holes so massive that to grow from a standard stellar remnant to their observed size, they would have needed to accrete matter at maximum possible rates for their entire existence, without pause. And in some cases, that calculation still does not produce enough mass in the available time. The technical term for the maximum sustainable accretion rate is the Eddington limit, and it exists because the radiation emitted by infalling material exerts pressure outward. At a certain accretion rate, that radiation pressure balances gravity and pushes the surrounding material away, effectively capping how fast the black hole can grow. Standard black hole growth models built around this limit struggle to produce billion solar mass black holes in the time available in the early universe. Webb has studied specific early black holes in detail. One system, a quasar called UHZ-1, was identified in 2023 through a combination of Webb observations and the Chandra X-ray Observatory. The data suggests this black hole had a mass between 10 million and 1 billion times stellar mass, when the universe was only around 470 million years old. If that mass estimate holds up to further scrutiny, the growth timeline is extremely difficult to explain through standard accretion alone.